Hey everyone, today let's try to solve a problem called maximum and minimum sums of at most size k subarray. So in the problem description it says you are given an integer array nums and a positive integer k, and you have to return the sum of the maximum and minimum elements of all subarray with at most k elements. So basically the subarray length should at most k, and we have to return the sum of maximum and the sum of minimum. Let's see one example to illustrate the idea. So in this example, the input numbers is 1, 2, 3 and k equals 2. It means the subarray size will not be larger 2, and the answer is 20. Let's see why it's the case. So here it kind of lays out all possible subarrays for the 1, 2, 3. You notice 1, 2, 3. This is also a subarray, but it's not listed in here because there is an at most 2 elements restriction there. So for this one subarray, the minimum is 1 and the maximum is 1, so the sum is 2. And for this subarray, the minimum is 2, the maximum is 2, so 2 plus 2 is 4. And for this subarray, the minimum is 3 and the maximum is 3, so 3 plus 3 is 6. And for this subarray, the minimum is 1 and the maximum is 2, so 1 plus 2 is 3. And for this subarray, the minimum is 2 and the maximum is 3, so 2 plus 3 is 5. So you can see this 2 plus 4 plus 6 plus 3 plus 5 in total, that will be 20. So that's why the answer here is 20. Yeah, this is not a very complicated problem in terms of the problem description. So the hard part is the constraint is a little bit large. For example, the num's length will be 80,000. So 80,000 is about 8 times 10 to the power of 4. Sorry, it's not about, it's exactly 8 times 10 to the power of 4, which is very close to 10 to the power of 5. So we cannot do an n squared solution here theoretically, and also the num's value is really large here as well, so I would assume using segment tree is also not possible. I guess that's the hard part of this problem. Yeah, but that's pretty much all for the problem description, and let's see how can we reason a solution out of this. Okay, so the key idea to solve this problem is to use a data structure called monotonic DAG for getting the last k element basically. So just a little bit of introduction. Monotonic DAG, it's a data structure that supports pop front and pop back usually. So in this case, we are going to keep the DAG monotonic. It means that it will be non-decreasing for finding the max, or non-increasing for finding the mean basically. So in that sense, if we are keeping, for example, if we are keeping the DAG as non-decreasing, so the front of the DAG will be the maximum, and vice versa. If we maintain a DAG that is non-decreasing, and the front will be the maxed. So anyway, we are going to maintain a monotonic DAG, and if the front index is less than the start, the maximum start that we are allowed using k elements, then we're gonna do the pop front, and we're gonna do the pop back for any numbers that are smaller than num size, because we want to keep the DAG monotonic, and after that we will push back for num size. Okay, so let's take a look how this would look like for this example. In this example, numbers equals to 1, 2, 3 and k equals 2, and the DAG would be something like this if we are looking at index 2 here, because this is index 0, this is index 1, this is index 2. So if we are looking at this particular index, assuming this is the DAG for non-decreasing, so basically it will pop anything that is smaller than it, and it will become 2 here, and you get the idea. So basically dq.front will be maxed or min if we are trying to look for the minimum, because we have to do this whole thing, this whole loop twice, once for finding the max and once for finding the sum of the min. So dq.front will be maxed, but that's not enough, because we also need to know how many times does it appear. Maybe I will give you a little bit more context. So basically, while maintaining a DAG, we are going through the elements from left to right, and for each element, for example here, we are basically trying to find all the maximum sum that ends with this index. For example, what is the maximum in here? It's going to be 3, 5. So the maximum is 5, and where's the maximum in this subarray is going to be 5 again. So you get the idea. So how maintaining our DAG would help us answering this question? So basically, if we maintain the DAG correctly, we know for a fact that if we're looking for a k-size subarray ending at this particular index, it would have dq.front as the maximum. Let's say this line is size equals k. Let's assume that there's a size k here, but we don't want to just look for size k. We want to look for size k minus 1 as well and size k minus 2 as well in order way to just want this one element. So, and if you think about it a little bit more, how many times will this dq.front appear? So I'm gonna write a small helper function which is called length lr, which will just return the length of this subarray where it starts at l and ends with r. So the formula for that is really easy. It is just hollow the ending minus the first and then plus 1. This is the formula to calculate the length of this subarray with this starting index and this ending index. For example, if it is 0 0 and then it is 0 minus 0 plus 1 will be 1, so it is correct. With this helper function length, we can kind of use this to calculate how many times does this dq.front, which is maxed, which is a dq.front. We want to know how many times does this a dq.front appear for the maxed. So the answer is we know the start, the current index is, for example, I is here. So it's going to be I minus k plus 1. If we're looking for dq front being the max and with the restriction of k, the earliest start is I minus k plus 1. And the first time this dq.front appear is, of course, dq.front. So this is the time that this dq.front, so dq.front is here. So this is how many times this a dq.front will appear for ending at I index. But that's not the end. That's just calculating the number of times for this a dq.front appearing. But we also want to know the next element for dq.front. So how many times will it appear? So apparently it will be dq.front plus 1, because after this dq.front plus 1, for example, this is the dq.front and dq.front plus 1 will be here, then we can no longer consider this element. So it will be dq.second front. I'm making up this API, but you get the idea. So basically it is for this dq second front. So if we pop the dq and then we access front again, it will be this dq second dot front, and we need to times this as well, dq dot second front, sec front. But we don't have to actually iterate for the whole DAG because that will cause too much time. But you can see a pattern here, except for the very first element, which is the maximum. Basically, all the other elements on the DAG would appear exactly dq.front plus 1 all the way to the current index that we are pushing. So we just need to do some trick to reserve that while pushing elements on the back. That's basically how we can calculate the max or the minimum, which is going to be very similar, but kind of inverse. And with that, we can achieve a solution with time on and for space and time as well. And I know it still seems a little bit complicated, and let's see how to implement it code. Maybe it will be simpler after seeing the code. Okay, so let's get started with the coding. First of all, we're gonna initialize the size of the nums as n, and then we're gonna need to write a helper function called length, which accepts L and R, in which it will return the length of this subarray. And then we're going to have another helper function, so it would accept a boolean value. So if the boolean value is _max is true, it will return the sum of all the maxes. And if it is false, it will return the sum of all the min of all the subarray, of course. So in this helper function, we're gonna declare the DAG as an empty DAG at the beginning, and also we will have an appear underscore times factor. So appears underscore times I will represent how many times would nums I appear as the maximum or as the minimum. It depends on if we are doing is max or not. If we're doing is max, is going to say how many times would this nums I appear as the maxed. Otherwise, it's going to be how many times would this appear as a minimum. So then we're going to initialize the answer and the current as 0, and then we're going to iterate the element one by one. So this line, if some elements in the deck is having an index even less than k, then we have to remove it. And because we remove it, we need to not consider these particular nums, and then also times the number of times that it appears, and then I'm going to pop it. So here, so we are going to maintain a non-decreasing queue or non-increasing queue, depends if we are going to search for the max or min. So if we are searching for a max, the condition will be while queue is not empty and the current value is larger than the back of the deck, and we'll keep popping the back, so to maintain a non-decreasing queue. Similar thing for min, the condition will be while the queue is not empty and then the current value is smaller than or equal to back of the queue, that we will just keep popping the back to maintain a non-increasing queue. So in any case, what we want to achieve from this is dq.from will always be the maximum or the minimum in case its max is forced. So as you can see, this first boolean is just dq, it's not empty, and the second one is more complicated. It looks more complicated, but it's just, if it is max, then I will use this boolean flag, and if it is not max, it means I should follow this boolean. So it's here. Okay. So if we're going to not consider it, we need to retrieve its value and times the number of times that it appeared, and then we pop it. So now we need to think about how many times would nums I, namely the new value, is going to be for being the max or the min. So because we already pop everything, that's why it will be non-decreasing or non-increasing. So in the future I, if we want to use the current I as the maximum or the minimum, the range that we can do is dq back plus 1 all the way to I, because like after dq back appear, I will no longer be the maximum or the minimum based on because the q is non-decreasing or non-increasing. So that is the case when the dq is not empty, and then you just push the I at the end of that. And these three lines, I would like to explain them at the same time because they are kind of related and not so obvious at the first sight. So let's look at this line first. The number of times for this dq front to appear, as we already explained, is going to be the I minus k plus 1 all the way to dq front. We do I minus k plus 1 because this is the maximum subarray size that we can get ending at I, which is I minus k plus 1, because we have the size limit of k. Of course, we cannot be smaller than 0, so it have to take maximum 0 and I minus k plus 1. And this is the left of the subarray that we can choose from, and the right of the subarray is going to be dq.front because it is the first time that it appears. And the length of that is the number of times that we can choose for the dq front as the maximum. And then we are going to plus these nums dq front times the appear times for this thing, because the appear times will update every time. So that's why we have to have this line 28 here. We have to remove temporarily the dq front appear times first, and then we calculate the appear times here. So if it is the first appearance, the appearance underscore time dq front will be 0, so anything times 0 will be 0, so this just does nothing in the 28 time, in the line 28, and then we'll update the appearance times, and we'll base on the appearance times and update the current. So, and this kind of handles case where I is exactly the dq.front, but we only take care of the dq.front, it could update. But in case I is not the front of the deck, we have to add nums I and it appears time as well. And after that, we're just going to add answer using current. And finally, we just return the answer. This answer is just for the utility function. So, but at the main function, we will just return utility true plus utility false. It's just, this one is to take care of the max, and this one is to take care of the minimum. And that should give us the correct answer. So the time and space complexity will both be on. And let's try to submit this to see if it works. Okay, accepted. Thank you so much for watching. And if you find this helpful, please like. And that's pretty much all for today. And leave a question if you find anything that's confusing. And I will see you next time. Bye bye.